This week, we're going to study harmonic measure, which is an important measure for complex analysis and partial differential equations. And in particular, we're going to study some results that lie at the intersection of these areas with geometric measure theory. Now, this is sort of a naturally occurring measure because it can be defined using sort of simple and fundamental concepts from several different fields. So I'm going to go ahead and give 3 different definitions of harmonic measure, all of which are equivalent. The first definition that we give is the complex analytic definition. So let's suppose we have a Jordan domain omega in the complex plane. Then the Riemann mapping theorem says that we can find a conformal mapping phi of the unit disk onto the domain omega. And in particular, for any point x inside omega, we can arrange for this conformal mapping to send the origin to the point x. Then there's a theorem called Carathéodory's theorem that says that this conformal mapping extends to a continuous map between the closures of these two domains. And so that means in particular that phi maps the boundary of the disk to the boundary of omega. Thus, we define harmonic measure for this domain with pole at x to be the push forward of normalized surface measure, so normalized one-dimensional Hausdorff measure on the boundary of the disk, the push forward of that onto the boundary of omega. So that means that the measure of some subset A of the boundary is just equal to the normalized surface measure of the inverse of this set. The next few definitions we give work in any Euclidean space, not just a plane. So let's suppose we have a domain omega inside some Euclidean space, a point x in omega, and a subset A of the boundary. Then we define the harmonic measure of the set A with polar x, which we denote little omega sub omega sup x of A. So we define this to be the probability that a Brownian motion first starting at the point x will first hit the boundary of omega in the set A. So we're not going to ever rely on this definition at all this week. However, I sometimes find that this definition of harmonic measure helps me understand the sort of intuition behind how harmonic measure behaves in practice. The final definition is the one that comes from PDEs, and it's the one that we're going to assume this week. So let's suppose we have a domain omega in Euclidean space, and we're going to assume that the boundary is regular, which means that we can always solve the Dirichlet problem. So recall that the Dirichlet problem, or the classical Dirichlet problem, asks for, given a continuous function on the boundary, to find a function, uf, that's twice differentiable in omega, and it's continuous on the closure of omega, so that it's harmonic inside omega, so its Laplacian is equal to 0 along omega, and moreover that if we restrict u to the boundary of omega, it's equal to the boundary data f. Okay. Now notice then that if you look at the map that takes a continuous function f on the boundary to its harmonic extension evaluated at some fixed point x in omega, this ends up being a bounded linear functional. So that means that the Riesz representation theorem says that there is a measure omega sub omega of x that depends on this point x where we're evaluating the harmonic extension. So there exists a measure such that uf of x is equal to the integral of the boundary function f with respect to this measure. Okay, so this kind of motivates why we call it harmonic measure, since in effect, this class of measures, as we vary in x, it's in some sense varying harmonically, in the sense that when we integrate this class of measures against a function f and then vary x, that is a harmonic function equal to the harmonic extension of the function f. And moreover, this gives us, in some sense, a way of being able to harmonically extend functions defined on the boundary that may or may not be continuous. For example, characteristic functions of sets. So now we've seen 3 different ways of defining harmonic measure given a domain omega, each of which is quite natural. So it's a very natural question then to ask, what is the relationship between the geometry of the domain omega and the properties of the harmonic measure that it generates? So we're going to focus on 2 sub-questions in this category of questioning. So the first one is when harmonic measure is absolutely continuous with respect to Hausdorff measure. So notice that if we have a domain in Rd plus 1, and let's say the domain has smooth boundary, then using techniques from like first year PDE course, you can show, or you can explicitly solve for what the density of harmonic measure is with respect to surface measure on the boundary of this domain. So in particular, for smooth domains, harmonic measure is absolutely continuous with respect to d-dimensional measure if we're working in d plus 1 dimensional Euclidean space. So we're going to investigate what happens for more general domains. The second question that we're going to consider is what happens when we know that harmonic measure is not absolutely continuous with respect to Hausdorff measure necessarily, but if it is absolutely continuous with respect to the harmonic measure on the complementary domain to the one that it's defined. So in particular, if we have two domains, omega 1 and omega 2, that are disjoint but have common boundary with each other. So they're sort of complementary. So for example, this could be omega 1 and this could be omega 2. What information do we obtain about the boundary if we know that the harmonic measures for these two domains are mutually absolutely continuous with respect to each other?